All right, so let's talk about some things. So we'll start again with this lovely concave mirror. So, and develop a system here. So one of the first things we do is we'd like to draw a lovely image on this thing, and we love drawing all these lovely light rays all over the place. So let's say I put a lovely object. So anybody know what the most famous object we put on here is? For whatever reason, it's a candle. So we just love putting candles for these things. So in this case, I'm going to draw some light rays coming off that candle. We're going to see where they reflect off this mirror and draw some conclusions from that. So in this case, one thing to note is with this concave mirror, it's important to note that right now I am beyond the focal point. That'll be important. So there's really 4 light rays we can draw. And what you can see is when light hits this lovely mirror, we have to kind of look at what the angle of that mirror is, and then look at kind of the normal to that. And we could say that the incident angle would equal the angle of reflection right at that point. So because the mirror is not flat, every point has a different pointing normal and stuff like that. So, but the principal light rays we draw is we first draw one coming in parallel to this principal axis, parallel to that principal axis. So every light ray that comes in parallel to that principal axis is going to come back out through the focal point. And so we're going to have a light ray being reflected right through there. And you can kind of see where here's this surface right here, and the normal will be coming right between those two, separating them with an equal incident angle and an equal reflected angle. Cool? All right. Then we'll have another light ray coming in through the focal point. And that one actually gets reflected back parallel to the principal axis. Cool. Another one you can draw is to draw one right to the vertex of the mirror, right on the principal axis itself. And that one's perfectly, vertical the way I've drawn it here. And so you'll find that that principal axis divides the incident angle and the reflected angle in half, or it makes them equal anyways. And this is going to come off. And you can see that all of these lovely light rays converge on a single point. That is where the image is formed, where all the light rays converge. If the light rays all really converge at a point, we'll find out that now we call that a real image. And we'll find out in this case then, if this thing was on the top side of the principal axis and now the image is on the bottom side, what you'd find out is that this lovely image is upside down. And so it turns out it's an inverted image. So, and we'll find out, we can put a parallel here that all real images will be inverted and all inverted images will be real. Real and inverted go together. So it's convenient that you can use the acronym IR, which is a type of light, if you will, electromagnetic radiation here, to kind of go together. And we'll see a different type here in a little bit. So it turns out with this concave mirror, as long as you're beyond this focal distance, you will always get a real inverted image. As long as your object is beyond that focal point, it'll work out that way every time. So what that really means in terms of this lovely equation here is that if your distance is, if the P is greater than F, what you'll find out is that your Q is always going to come out to be positive, first of all. And a positive Q means it's a real image. Whereas a negative Q would mean it's a virtual image, and we'll see that as well. Cool, but that's the deal. So you also find out that as long as you're beyond this focal point, again, you always get a real inverted image, but as long as you're within the actual radius, so somewhere in this region right here between the focal distance and the radius of curvature, so your object will appear bigger. Your image will appear bigger than the object, and look, it kind of even looks bigger. You'll find out that once you get beyond the radius of curvature though, then the object will appear, then the image will appear smaller than the object. What do you suppose is true if you're right at the radius of curvature? Yeah, your image is going to be the same size as the object. So that's kind of how that works. Cool. So, but that's one situation. As long as you're beyond that focal distance, you get a real inverted image. Sometimes it's bigger, sometimes it's smaller, depending on which side of the radius of curvature you're on. Okay. The second situation we've got to deal with is when you're within the focal point. Let's make our lovely candle again. I'm not really good at making candles with flames here, so have to forgive my lack of artistic ability here. Draw cyclohexane chair conformations like nobody's business, but anything else I'm kind of screwed. So in this case, we're going to draw very similar looking light rays. So what was the first light ray we drew with our other situation here? Yeah, one coming in parallel to the principal axis. And where did that one get reflected? Through the focal point. That hasn't changed. Cool. Now we're going to have one going through the focal point, but I can't do it. I'm past the focal point. So what we're going to do is we're going to approach the mirror as if we'd come through the focal point. And so in this case, it's kind of like here and then keep going. And where does that one come out? Yeah, that one comes out parallel to the principal axis. And finally, if I want to, I can draw one. Notice it doesn't really take 3 light rays, or even 4. There's a 4th one we could draw if we wanted to. It only takes 2. Once you get 2, you can see if they intersect or where they intersect or all that stuff. So in this case, I can draw one to the vertex on the principal axis, and it reflects down below. Do these light rays ever really converge? No, then there's no real image here. What you can say, though, is they all look like they came from a common point behind the mirror. Were there ever any light rays back here behind the mirror? No, there never really were. And so we call this a virtual image. There's no real image there. It's virtual. And in this case, if you notice, it forms above the principal axis, which means it's not going to be an upside down image like we had here. So it'll be upright. And again, another mnemonic, U and V here go together. And again, convenient is UV is another type of light, another part of the electromagnetic spectrum. So UV and IR. So again, real images are always inverted, and virtual images are always upright. Everybody cool with that? Cool. And this is not just for the concave mirror. This is for all the mirrors and lenses we're going to deal with here. Cool. And it turns out as long as you're within the focal distance, you will always get a virtual upright image. The fact that it is a virtual image means that your Q, or your distance to the image, is going to be a negative number. So the fact that it is upright means that your magnification, when you plug it in, is going to come out positive.